break, or at least test whether it is breakable. And as I was saying earlier, A51 is academically broken, that is on a statistical level shown to be insecure if you have vast amounts of key stream. However, the way it's used in GSM with just a very small chunk of key stream, it's not attackable. Instead, we have to resort to generic attacks that could really break any encryption function if the secret key is small enough. Now with A51, the key is small, but just a little bit above the practical barrier for straightforward, naive, say, brute force attacks. 64-bit key would take you a while. Straightforward implementation, about 100,000 computing years on a standard PC, or 1 year on 100,000 standard PCs, rather. So that's not much compared to the trillions and trillions of years you'd need to break RSA or AES, but still out of the reach of most people. Which is why we need another approach towards breaking this. And the key here are time-memory trade-offs. And the idea leading up to time-memory trade-offs is a codebook. A codebook works the following way. You compute a data set where you know that some data item will be encrypted every time you see a conversation. So you take this data item and encrypt it under every possible key and store this in a table, along with the key you used to encrypt it. You sort that by the encrypted data package. Now, next time you see a data package, this encrypted data package on the air, you just use this lookup table to find the key that encrypted it. Easy enough? Again, that works for small key ciphers, and A51 is just a little bit above where this becomes impractical, since just writing out this table is somewhere in excess of 100 petabyte. So Google may be able to do it, but we are not. So we need to do two things to make this practical. First, we need to be able to compute this data set much faster than 100,000 years. And then we need to be able to store it in some compressed form in a much more practical than 100 petabyte form. Right? And that's the two dimensions of improvement that I want to discuss with you now to show you the process leading up to then actually decrypting a GSM phone call. Let's focus on the speed of generation first. We did improve, and this is now about a year of engineering. We did improve this cracker over and over and over again, the table generation of it in particular, through massive parallelization within single machines. GPUs is the key word here, through changing the algorithm to be parallelizable much better, and to finally find a shortcut in A51, and then after all exploiting a statistical property of A51 to make this a lot cheaper to compute. As our target, we are using GPU chips on graphics cards as our optimization target. They're almost as efficient as FPGAs, but much easier to program and much more available. So GPUs give us vast parallelization potential. You can stick up to 6 GPUs into a single PC, 3 PCI Express cards with 2 GPUs each. On each of these GPU, there's up to 60 computing cores. So where your Intel processor has 2 or 4 maybe, each of these has 60. Very small, but still independent computing cores. And to further increase the level of parallelization here, we apply a technique called bit slicing, where you are taking chunks of data from several data streams, stuff this into one data word, and have an operation be executed on the entire data word. So it's what back in the day was called multiple data single instruction. That same idea in cryptography is usually referred to as bit slicing. Taken to the extreme, you just take a single bit of each of your data streams and stuff all of this in one data word, which can be up to 256 bits. So really in a single instruction, you're doing something to 256 data streams in parallel on each of your 60 cores, in each of the 6 GPUs in your one computer. So there's really 100,000 computations going on in parallel while we are computing these tables. Almost the same degree of parallelization can be reached for the cracking phase. Not quite as trivial to implement, though. For the generation, this was fairly straightforward since the computing streams are independent of one another. Now this is the dimension in which we optimized for parallelization. Now I said we did also use one statistical property of A51 to further optimize this. And I believe nobody else is exploiting this yet. There are commercial A51 crackers on the market, and just from the price, the power consumption, or resource consumption, it appears that nobody is using the shortcut I'm about to describe. A little bit of background. So most stream ciphers back in the day were built from linear feedback shift register. Linear feedback shift register is basically a counter mod a number, a sequence that goes through all numbers within a range and then wraps around, and again goes through the same numbers in order and wraps around. So it starts at some number, and if you compute the function on it, it reaches some other number. You compute a function again, it reaches some other number, and eventually the circle closes after you've gone through all the numbers. That's a property of a linear feedback shift register. So if A51 was built from one, this circle would have a size of 2 to the 64 numbers until it wraps around. Now, A51 isn't built from this, because early on people understood that linear feedback shift registers are statistically broken. You can use set solvers, you can use linear approximation if there's bad filter function and all these things to break these. So this is disqualified to build a stream cipher on. What people are using instead is what they now call a non-linear feedback shift register. And that's what A51 is built upon. It is an LFSR that's clocked irregularly, though, and that makes it a non-linear feedback shift register. Non-linear, in the simplest definition, means there's several inputs that lead to the same output. For instance, an AND function is nonlinear. There's 3 inputs that lead to the same output in an AND function, right? So whenever you see ANDs or ORs being used, or non-regular clocking, that becomes nonlinear. Now, the result of several inputs mapping to the same output is that some values in the output range can never be computed, right? Pigeonhole principle. So really, if the input range is the same size as the output range, some values will never survive the first iteration. Some more values will not survive the second iteration. And as you keep computing the same function on this number range, the set of possibilities keeps shrinking. So shown visually, we still do have a circle. But that's, well, in this case, in fact, I think it's several circles. However, there's branches of the circle of values that do compute the same output, but that are not part of the circle. They will never be reached again. Does that make sense? So the circle in the middle is much smaller, and it's still a circle in itself. But there's some values, the other inputs that lead to the same outputs, that are just not part of that circle. Now in GSM, they do us a favor. They do compute A51 100 times before using the first outputs of it. So you do the first 100 steps in this scheme before any attackable output is generated, meaning every output that's up to 100 steps away from the circle, but not actually on the circle, will never be used to generate a GSM output. All these extra states around it are irrelevant for breaking A51 in GSM. And the circle inside is only something like 2 to the 61. So that's an 8 times improvement of both attack time and storage, meaning if you keep your storage constant, you're improving by more than a factor of 30 your attack time. Right? And that's a statistical vulnerability of A51. Some newer ciphers, they intentionally use a larger state size than the secret key size, acknowledging the fact that, in fact, their state will collapse onto some smaller number. And in fact, even some ciphers that are used by GSM phones use this, but not A51. So we can exploit this much easier than we thought. And in fact, we only added this improvement after our Rainbow table release in December. So we computed a completely new set of tables during the month of April on merely 4 computers that's now available on BitTorrent as of today. Now that's how we make sure we can compute it in feasible time, by parallelizing the computation and by computing much less than from the outside appears necessary. So we can compute it on 4 computers on 1 month. Now this slide starts getting into how we can store it smaller. Even 2 to the 61 values written out is still something, I don't know, 20 petabytes, still not very feasible. So the key here is what I call time-memory trade-offs, a way to store a code book compressed. Now recall the code book was a set of keys and the outputs it would generate. Ordered by that output. We want to be able to store this set much more compressed so it would fit on what we can share over BitTorrent, in this case 2 terabytes. Or that we can at least share over postal mail, which is how we've been doing it so far. And here's how we would do this. Instead of computing just one hop from one key to the output, we're computing several hops in a chain of computations. So each of these Ks is an A51 computation. Of these chains, we only store the very first and the very last element in the table. So if this table still covers all the 2 to the 61 values, the wider the table becomes, the less you have to store, since it's shrinking in height. Now that's the one side.